In today's lecture, we're going to go over briefly what we covered yesterday in a more just straightforward manner, and then we're just going to keep on building. Yesterday, we learned about Coulomb's law, which helps us understand how much force one particle has on another. And that's just KQ, Q1, Q2 over R squared. Big Q is the absolute value of little q. So Coulomb's law is always positive. But there's an electron. No, it's always positive. You take the absolute values of the charges. So if you've got two charges, the question would be, what is the force on either of these particles by the other particle? Then you have situations where you need just the electric field. For a point charge, it's asking as if we have a point charge at this point, and at that point, what is the electric field at that point? We use E, K, Q over R squared. So it's just without the other charge. Because if you have a charge sitting here, it is affecting the other point. It's changing, it has a certain electric field at this point due to the charge here. Sort of like, probably the equivalent would be, if we're not here in the room, gravity still works with the magnitude of 10 meters per second down. But if we walk into the room, now we have a force pulling down on us. So gravity is kind of like electric field. And the force of gravity pulling down on you is like Coulomb's law. Now for a point charge, it's like this. But you can have a room of E field that is uniform, and it's basically whatever we say it is. It could be, typically we just go left to right, right to left, up, down, stuff like this. And it's typically usually given or solved through some means. In these point charges and in the Coulomb's law, there is a relationship saying that force is equal to the electric charge or the electric field times Q, the magnitude of the charge. This works for both sources of E that are points or rooms. If it was a point, that E field would come from here. And if it was a room of E field, so like we talked yesterday about the capacitors. Capacitors have uniform electric fields, and all you would then have to do is, oh, give me the charge, give the magnitude of the E field, and then boom, there you go. But if you have a point charge and you put another point charge in the room, then you have to use Coulomb's law. Now, we studied how positive and negative charges, their E fields are interesting in terms of how they look. With positive charges, their E fields radiate outwards, and the further you get, the weaker they are. Likewise, if you had a negative charge, their E fields point inward, but as you get further away, they get weaker. And it all depends on the direction of the E field at a particular point. Basically what you do is you draw a line to that point. And if it is a positive charge, the arrow goes outward. If it is a negative charge, the arrow goes inward. So it's kind of, it's some simple stuff. Positive charges feel force in the same direction as the electric field. Negative feel force in the opposite direction as E. So if we had an electric field going from left to right, and we have a particle that feels a force in that direction, is the particle positive or negative? I just got done telling you. It's positive. It feels the force in the same direction. If I had a negative charge, would it go to the left or to the right? With this E field, it'd go to the left. A simple example that I use in terms of studying the electric field, I'm not known for, well, except for pufferfish, violence against animals. Otherwise, I just annoy them greatly. Let's say that in this room you walked into Lewis Hall and there was, it's going to look more like a pig. There's a pretty little cat, a little kitten, and the kitten is suspended in the air, floating. No strings, no nothing. Just a cat looking bemused or amused at the fact that it's just sitting there in the middle of the air. One of the things that you could ask is, well, is that cat moving up or down? I go, it's doing nothing. It's just sitting there. Is it resting on anything? No. It's just the air and the cat. So what do I know immediately about the situation? What a core equation that you learned in 213 for objects that aren't doing anything? Some of the forces are equal to 0. And in this case, we will say just vertical only. Now, obviously, it's in Lewis Hall, so it experiences gravity, which means it will feel an F sub g, which is equal to mg down. Now, a couple of questions. I don't really know. The kitten, 1 kilogram. So we have a 1 kilogram cat, or kitten, suspended in the air. Now the question that I have for you is, I'll give you the electric field strength to be 1,000 newtons per coulomb. What I want to know is, what is the charge? And the charge could be positive or negative. What's the charge that the cat has to have in order for this cat to levitate? And I need to give you one bit of information, that the electric field goes from floor to ceiling. So it goes from bottom to top. So for this particular cat, first question that we have is the cat positively or negatively charged? What force are we going to use? Well, we're going to use F is equal to QE. So if the electric field is pointing upwards and the gravity force is pointing downwards, which direction does the electric force have to go in order for it to balance? It has to go up. So the electric force goes up while the gravity force pulls down. So if I need an electric force that is pulling up to oppose the gravity force which is pulling down, is the cat positively or negatively charged? It has to be positively charged, because in order to feel a force in the direction of the electric field, it has to be positively charged. The sum of the forces is equal to 0. It's not moving up or down. The downward force minus mg. The upwards force is QE. Therefore, mg is equal to QE, and Q is mg over E. So m is 1, g is 10, electric field is 1,000. So there is 0.01 coulombs, or you could say 10 millicoulombs on that cat in order to keep it levitated. So we were using some basic equations. F equals QE, the gravity force, the sum of the forces is equal to 0. This term, translational equilibrium, we have used in so many different problems. Determining normal force, determining friction force, torque bars, inclined planes, Atwood's machines, and now we're once again using them in just charge problems. If it's not doing anything, that's so awesome, because you know something about it. You know that the sum of the forces is equal to 0. So if we had one simple charge or a room of charge, we're able to manipulate it. And one of the things that you guys will be doing today is studying the appearance of electric fields in situations where there are multiple charges or there are different arrangements of charges. To understand how this goes, we're going to have to introduce the idea of potential. And eventually, we're going to get to potential energy. Now, the way that I equate potential and electric potential is I make it similar to height. If you're way up on a mountain, you're at high potential. If you're way down in a valley, you're at low potential. The big difference is that in a gravity situation, that has a high potential energy. And there are situations where if you have charges, let's say we had two plates. One is insanely positive and the other plate is insanely negative. If we put a positive charge here and a negative charge here up against these plates, this charge will go to the negative plate and the negative charge will not do anything. It'll stick up against the plate. Likewise, if we have a positive here and a negative there, it will be the negative charge that moves and experience a force that causes it to accelerate, while the positive charge just sits there because it's bumping up against the plate. What we have is, with high potential, it has the potential to have energy if things work right. In this particular case, the positive plate has high potential, and the further down you go, it has low potential. And you can think of it as a high height and a low height. Now, with positive charges act a lot like mass. If you have mass on top of a hill, that mass is going to come downhill. So positive charges will go down the hill. But what's a little bit counterintuitive is that if you have a high potential area and you put a negative charge there, negative charges will not go downhill. But what they will do is that negative charges they will go uphill. So it's a horrible word to use. I really shouldn't use it, but it's a lot of time, well, people say it's theoretically possible. Negative charges is like anti-mass. Mass that acts in the opposite direction of gravity. It's like if you had a mass at the bottom of the hill and you just let it go and it rolled uphill, that would freak you out. But a negative charge will move to higher potential naturally. It just acts in the opposite direction that a positive charge would behave. Positive charges act like you would think mass does. Negative charges act in the perfectly opposite direction of than what you would think they do normally. And the high potential is associated with the positive charge, so it kind of makes sense. The low potential is associated with the negative charge. Negative charges are repulsed by negative particles, so they get repulsed or uphill. The negative charges will get, the positive charges will be repulsed by high potential or positive charge, and they will go downhill. So if you had a positive and a negative charge, they're similar to hills and valleys. That the positive charge is the hill and the negative charge is the valley. And this brings us to the equation that we use for potential. That potential is KQ over R. V is the symbol for potential. K is that constant that we've dealt with. R is the distance from the point to whatever point charge we're dealing with. And this is, and I should write this down. This is V for a point charge. KQ over R. And Q is the charge. And it is possible for it to be negative. So let's go over the three big equations that we've covered so far, and this one is the third. Coulomb's law, can it be negative? No, it is always positive. Electric field, can it be negative? No, it cannot be negative. The potential can. Whereas Coulomb's law is used for a force, which is then used for a vector. Vectors are traditionally used as a magnitude and direction. Now granted, when we did problem set 3 and 213, where we added all those vectors together, and there were the snarky vectors, -3 meters at -90 degrees, the first thing we had to do was convert it to a conventional vector, a magnitude and a positive degree. So vectors, the naturally occurring vectors, the non-snarky vectors, are all positive. Electric field is also used for a vector, so we want that to be positive as well. Once again, vectors do not have negative magnitudes. Just can't have a negative magnitude unless you want to be snarky about it, and we try to avoid that. Potential is a scalar. It's a value. It could be positive or negative. So positive, 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 or negative. So a scalar, you can have it as a positive or a negative value. Just as you could say you have a positive or negative altitude. Mount Everest has a high y that's greater than 0. The Dead Sea has a low y. In fact, it's so low that it's less than 0. There are many places on Earth that are actually beneath sea level. Sea level is the equivalent of sea level in potential is where V is equal to 0. It is a reference point. We make sea level in geography the reference point because it's just the most sensible thing to do. You're either above the water or beneath the water. It's kind of a fundamental status of existence on this planet. But it doesn't have to be at sea level. We could set the reference point to be Oxford, Mississippi. Oxford, Mississippi, when compared to the sea level, is 500 feet. But if we declare Oxford to be 0 feet altitude, then sea level would be -500 feet. It's all dependent upon our reference. It is a reference point or origin. It can be moved. Now, typically with a hill and a valley, if you've got a high point and you got a low point, you could set your reference point to be in all sorts of places, but typically what we do is we set the reference point to be at where potential is 0. And we use that we treat that kind of like our sea level. Going back and continuing with this hill and valley, if you've ever done orienteering or you've done just using a topographic map, one of the things that you see is you see these height lines. And if you have a hill, you have a valley, these lines are exactly where the height is of a particular height. The one that I use, it's like highest point in Lafayette County is up on Thacker Mountain south of here. And so you could see the circles getting ever smaller until it reaches the highest point. So this is the highest point in the region. The lowest point is in a valley. So I don't know, there's probably, I mean, the only valley I can really think of is where like Sardis Lake is. Is there a lower point than the surface of Sardis Lake? Geology majors? I don't know. I leave that as an assignment. But there are valleys, and so this is kind of like the pit, the edge of the pit, deeper into the pit until you get to the lowest point in the pit. If we have a pebble, let's say a positive pebble, that pebble will start at the positive end and move straight across to the negative. So if we released a pebble at the top of the hill and it's on the side of the hill that's facing towards the valley, it would just head straight for it. If we put the pebble here, it would go and bend like this. And if we put the pebble there, it would bend like this. And if we put the pebble there, it would probably roll out for a little while and then come back and swing around and do that. And what you end up with are a whole bunch of lines. These lines right here are equipotential lines. These red lines are the E-field lines. Now, the way that they're drawn right now is they are drawn in a continuous fashion. Really what you do is, if you wanted to know the E-field at that particular point, you look at where the line is headed at that particular point. The line is headed pure right, so the E-field at that point is greatly to the right. Over here, you look at the slope of the line and it's actually pointed in that particular direction. If you put your point here, the slope of the line is aimed at that direction. So really, when you're working with the lab today, you're going to have this. You're going to have a black sheet of paper. You're going to have two like metal thumbtacks tacked into this special type of paper, and you're going to end up drawing something like this. And I'm going to teach you how this thing works. You're going to have like a little plastic rectangular object, and you're going to have this is a digital multimeter. Your digital multimeter will be your friend for the next 3 weeks. The digital multimeter measures all sorts of things, including what we're going to measure today. It's going to measure potential difference. Was it in June when we had Siri say to the class, "I'm sorry, I don't understand what you're saying"? Okay. That was summer here? Okay, that's what I thought. So you've got this digital multimeter, and so you're going to be measuring potential difference. Let's kind of talk about potential and potential difference. Now, potential, think of if we had a hill, and potential V, and let me just introduce all the parts. This V, its unit is V itself, and that means volts. And volts is used for potential and potential difference. Now, potential and potential difference, in my opinion, and once you get a firm grasp of what it is, you basically say, well, there's no real difference between the two, potato, potato. If we were at a specific potential here, that means we're at a specific altitude compared to 0. So this, we could say that this is a potential of 10 volts, because when you measure the difference between that point and your ground point, that's a difference of 10 volts. Potential is the same as potential difference because it's measuring the potential difference between that point and the base ground, the reference point. A potential difference kind of the definition is the word itself. The potential difference is the difference between any two potentials. Potential is the difference between any point and ground. Ground being where the potential is 0. So effectively, it's the same thing. Effectively, potential is a subset of potential difference. Potential is just clarifying the fact that one of the reference points is 0, and then the other one says that both of them are non-zero. And so potential difference, they typically write delta V. Potential, they write V. Delta V is V final minus V initial. And when you look at this and you go, well, if you start at ground, V initial is 0. So VF is just wherever you end up, whatever that final position is. And what you're going to do is on this board, the first thing that they're going to do is you're going to use the thumbtacks. So the two tacks are on this black sheet of paper. You hook it up to the positive and negative ends of the power generator. And what this does, they tell you to set up a potential difference of I think it's 5 volts. So at the positive end, your point is positive 5 volts. And then at the negative end, because this is effectively ground, you set it to 0 volts. So this is the board that you're dealing with. Now, the digital multimeter has 3 plugs. And let me warn you about the plugs. One is I think it's red, black. And for the most part, you're gonna use just one of the reds and always the black. The second red is for high current. And we'll talk about that later. It is most often not used. So there's a middle, I believe it's the middle plug and the plug on the right. One is red, one is black. You're gonna have 2 probes. These probes are effectively little tiny ice picks at the end of a wire. Each wire has a color. You put the red one in the red port, you put the black one in the black port, so that you need, and then so you know which one is which. And then you put one of the probes, there's 2 little holes in this chip. You put the black probe in one of the holes, it doesn't matter which one, and you put the red one in the other. Now, the interesting thing that they've set up in these probes is that the distance between the 2 ends is 1 centimeter. So you know for a fact what the difference is in position between those 2 points. Now comes the equation. When we look at all this stuff, it's a continuous line. It is something that if we put a point there, we know that the E field will point in this particular direction. What this does is we use the relationship delta V equals ED. That is the equation that you're going to use the most in this experiment. You can rewrite this equation to be delta V divided by D is equal to E. So an electric field is newtons per coulomb. Delta V is in volts, D is in meters. So you can have the equivalent that 1 volt per meter is equal to 1 newton per coulomb. So you're going to take these 2 probes near this big positive charge, or the positive pin, and what you're going to do is you're going to take it, and it doesn't, what you're really looking for is you take one of the pins, it could be the red or the black. I'll use red because it will then give me a positive number. So you take this, so the red pin is the red lead and the black lead is the black pin. Put your red pin closest to the red port, and then what you're going to do is you're going to take this and then you're going to rotate around. What's going to happen is that your digital multimeter is going to give you a number, and you rotate one lead. Hold on, that's dying. So really, I'm kind of exaggerating it. You put one lead down here, the other lead in the plastic bracket is like this, and then you sit there and then you rotate one of the pins around the other. And what you're looking for is, look for the biggest difference. So if I could tell you right now, if I did the pins like this, the potential difference between those 2 points is 0. The biggest difference would be something like measuring it like this, or like this, or like that. These E-field lines they are equivalently the slope of the hill. Where the change in V is the greatest. So the electric field is equivalent to the change in potential over the distance. Change in potential over the distance is a lot like you're walking on a hill. Your altitude changes 1 meter for every 10 meters you move forward. That's a slope. So the electric field is the equivalent to a slope of a hill. And what you're going to do is you're going to put these pins down and you're going to find the direction of the greatest change in potential or greatest slope. And depending on where you start, you can go in all sorts of different directions. And so what you're going to do in lab today is you're going to study, one of the things that you're going to do is you're going to study that, and you're going to draw a pretty picture, and you're going to figure out that if this is 5 volts, then this is 4 volts, and then this is 3 volts, and this is 2 volts, and etc. until you get to 0 volts. These lines here are equipotential lines. They have the same potential. If you measure that to be 2 volts, then over there has to be 2 volts as well. If that's 2.5, then that better be 2.5, and so on. And so really what I'm doing is painfully going through this, so when you're in lab this afternoon, and when I think about Friday afternoons before a 4-day weekend, I think nothing other than, great, we're gonna have lab. That's gonna be awesome. So, the other thing that they do is they put these metal braces down on the black paper, And so everything here will be 5 volts and everything there will be 0 volts. Now, when it comes to this, they're not really interested in you figuring out what's going on over here and over here. They basically want to show you that an arrangement like this is very similar to what we talked about today and yesterday with the room of equivalent E field. What you're going to do is you're going to do the same thing that you did before. Drop your reference lead, measure the location of greatest difference, and what you will find out is that those E field lines go like this. That between the two plates, they are uniform. Now what you'll find out is towards the edge, the electric field will start bowing out. For our purposes, what you do is you just initially show them beginning to bow, and then you don't care about what goes on over there because it's not really useful to you. And then what you see is that the equipotential lines do something like this. So the equipotential lines are like that, and then the electric field lines are like that. So in the lab today, you're going to do 2 different types of pictures. There may be a third. I forget if there's a third or not. But the technique is the same. You're going to take big advantage of that equation right there. And so what I need to do is use that equation for a few things that we're going to talk about now. And that is and depending on how far we get through the lecture today, I may yank out, let's see the homework real quick. We may not get to the second page of problem set 2. If we don't get to it, I'll postpone it till Friday. But the first page we're effectively doing right now. If we have a particle that's dropped, doing a simple physics 213, and we initially drop it, it's under the influence of gravity, and I want to know what is that final velocity at the bottom. You go, oh, this is great, I'm all over this. Do I use the equations of energy or do I use the equations of motion? Energy, it's the fastest thing. And so what you do is you understand that at the top, it has a potential energy that is entirely gravity, which we will call mgh. At the bottom, it is all kinetic energy, or 1/2 mv squared. Now, obviously, a question that could be asked is there friction in this situation? Answer, no. So everybody should go, yay, no friction. Because that means with no friction that the energy initial is equal to the energy final. That means that mgh is equal to 1/2 mv squared. The m's cancel. I'm left with 2gh is equal to v squared, or v is the square root of 2gh. So whatever numbers I pick, there you go. Now, what I'm going to do is I'm going to take away gravity and I'm going to set up a uniform E field. A uniform E field that is basically 20 newtons per coulomb. And I'm doing these numbers dynamically, so I don't know how well they're going to work out. I'm going to put, this is a positive plate, this is a negative plate. This is a positive charge where the Q is 400 millicoulomb, and I'm going to give it a mass of 0.01 kilograms. Now, initially what I could do is simply ask for what is the acceleration? What's the value of acceleration in this particular setup? And we know two things. We know that F is equal to ma, Newton's second law, and we also know that F is equal to QE. If you have a charge and that charge is moving, then you're going to use those two equations a lot of the time. Particularly in the front page of that problem set and then in the previous problem set. You have charges moving through an electric field. So we can get that A is equal to QE over M, which is 0.4 times 20 over M, 0.01. And we're going to have an acceleration that is 800 meters per second squared. So the acceleration is really, really quick. The question that I'm really interested in is, what is the velocity the moment before that positive charge impacts the negative plate? So we know that the electric field is continuous, it's uniform. The equations that we need are based upon, or some of them are based upon, this distance, which we will call 0.2 meters. So the two plates are roughly that far apart. Well, I have an electric field and I have a distance, so I can calculate the potential difference between the two plates, and that will give me delta V is equal to ED. So E is 20 newtons per coulomb, distance is 0.2, and I get 4 volts. Because an electric field times a distance will give you a potential difference, or just a voltage. So this left plate here has a potential of 4 volts over that plate. Its height is equivalently higher than the other plate. The potential energy due to a charge in a potential field is equal to Q delta V. So if we just take the charge and multiply it by its potential difference, we have the potential energy, which is in joules. Effectively, we're setting up the same type of problem. Rather than dropping something from a particular distance, we just have something move across a particular distance with an electric field associated with it. So what we do is we have Q 0.4 coulombs, a potential difference of 4, so this gives me 1.6 joules of potential energy, which means at the end, so the potential energy is this, the kinetic energy will also be 1.6 joules as well. Because there is no friction. Yay, no friction. Well, this is similar to a problem that we did before. We could set that the 1.6 is equal to 1/2 mv squared and solve for v. Now remember, this is something that I need to cover right now. The way that I draw a capital V is the lines tend to be straight and meet, and a lowercase v tends to look like that with a little bit of a wavy line. Everybody draws things differently. There was one dude, Grader, who had a mutant 4 that I just didn't understand. But this is the way that I draw V's and little V's. The other way that we do it in the, if we're going to do it in the alphabet soup method, is the potential energy is equal to the kinetic energy. And so the potential energy here is Q delta V, and the kinetic energy is 1/2 mv squared. This becomes 2Q delta V over m v squared, or v is the square root of 2Q delta V over m. Hold on real quick. Okay. Just to say out loud for the record, the 213s in June, there was a particular Friday where like, hold on, 40% of the class showed up? About 40%. I don't punish students for not showing up to class. We got videos and stuff like that. If any more of you just get up and leave, which is okay, don't get me wrong, it's a 4-day weekend. My weekend's gonna start in about 55 minutes. That particular class, I may not do it today, I could do it later. Pretty much everybody in the class in June got a 2-point curve on their final grade. Everybody. Except for the people who attended that one class, they got 3. I do reward those for those who stick in for the rest of the day. Not mad. Just letting you know. So we get this, and so we could plug in 0.44 over, what was the mass of this thing? 0.01. And the velocity square root of 320, and I get 17.9 meters per second. So what we did here was for a room of uniform E field, we use the equations delta V is equal to ED PE is equal to Q delta V, and then for the last bit we used PE is equal to KE, which is equal to 1/2 mv squared. And so if you have a room of uniform E field, that is what you do. You figure out what the E field is, you figure out the distance that it traveled, and then you start plugging it in and working it through this. And because there is no friction, you use the conservation of energy. And in most of these problems, I mean, I've never gotten to a level of confidence with my students where I could start throwing in friction into something like this. But, so there's going to be no friction in any of this unless I start doing problems with them. There is another type of problem, and these problems are used on the front page of problem set 2. And that is if you had a big charge. And in this case, I'm going to use big charge Q, not as a magnitude, but as a it's just a big stinking charge. It's fixed to the ground, even though there is no gravity. And I have an itty bitty charge where the initial velocity is 0. And I want to know at a very far distance what is that final velocity. The initial distance, I will say, is the initial R, we can just say R naught, is 0.1 meters. Now they have to repulse, so this big Q, I'm going to make it 0.5 coulombs, and little q is going to be 0.001 coulomb, and I'm going to make the mass of the little particle 0.1 kilograms. So this one is fixed. This one is allowed to move freely, and there is no gravity, so I don't have to worry about that thing getting pulled down. But I release it, so immediately it's being repulsed by the big Q, and it moves further away and accelerates. Now, if we had calculus at our disposal, which we don't, we could do a whole bunch of calculus to determine like the acceleration at various points and figure out the velocity at certain points and get all sorts of fun information. But because we don't, and I'm only asking for velocity, we get to use the energy equations for this. Now granted, up here, the acceleration is great. The velocity is small. What about the potential at this point due to that big Q? It's going to be non-zero. It's going to be fairly substantial since it's fairly close. But as it moves away, what happens? The potential drops. The acceleration drops. The velocity increases. So really, at a very far distance, that R is equal to infinity, effectively. So what is the potential due to that point charge here at a very far distance. What's the potential for a point charge? KQ over R. What happens when R is infinity? V becomes what? Zero. Because 1 over infinity is effectively 0. So this goes to 0. Here, it has high potential energy and low kinetic energy. Or actually, not low, no kinetic energy. Over here, it has high kinetic energy and no potential energy. Because what is potential energy? Potential energy that we'll be using is just Q delta V. Effectively, it's in this particular case, the delta V is just the potential. And the kinetic energy is 1/2 mv squared. So in this particular case, there is conservation of energy. The potential energy initial is equal to the kinetic energy final. The potential energy initial is Q delta V. The kinetic energy is 1/2 mv squared. So what is the delta V that we get to use? This particular delta V that we're figuring out is the delta V for a point charge, not for a room. So this equation here is for a room only, or in the case of the lab, small distances. So over small distances, you can say that delta V is equal to ED. But in this particular case, we're talking about a point that is very close to a point charge, and then it goes clear over to the other side of the galaxy or wherever. So you can't say that, but we get to use for a point charge, the potential V is equal to KQ over R. This V is the potential difference when compared to V equals 0. So in this particular case, we could say that this delta V is equal to KQ, KQ over R minus 0. So we don't have to worry about this. And in the end, we're only really interested in all these magnitudes anyway. So this becomes little q k big Q over R is equal to 1/2 mv squared. So 2qk big Q over R, m is equal to v squared. Which gives us 2qkq over r m square root is v. So this becomes 2 times 0.001 times 0.5 times 0.1 times 0.1. And I get it would take forever to get to this fast, 0.316 meters per second. So if you had that charge 10 centimeters away from the bigger charge and you let it go, its maximum velocity that it would attain is roughly 1/3 of a meter per second. The fun thing about this, to you guys it's been fun, me it's interesting at least, is that this particular equation there is no difference between these values here and those values there. Those two situations, yes?
Did you put K in?
No, I didn't, thank you. Did you recalculate for me?
No, I didn't. I don't have calculator.
Oh, you didn't bring a calculator to physics class. Okay. So there is a, what's K? 9 times 10 to the 9th. All right. So it's going to be a little bit faster than that. Hold on. So instead, okay, now I can believe this. 30,000 meters per second is its final velocity. Now, what I've illustrated here, what we've done is the upper problem, where given an initial velocity of 0, you let go from a big charge. That little charge experiences a particular potential due to the big charge. And at a very far distance, it has a particular velocity of 30,000 meters per second. But let's change it around. Let's say initially, you have an object being fired at 30,000 meters per second at a big charge here. How close does it get before it comes to a stop? It's the same problem. Instead of the potential energy being initial, Q delta V, it's potential energy final, Q delta V. Instead of kinetic energy final, it is kinetic energy initial, which is 1/2 mv squared. It's just flipped around. So you throwing the ball at me, let's say I'm the big charge and you throw a ball that's charged, it would throw it to me, it would come to a stop. And I would say, well, how fast did you throw it? Oh, I threw it 10 meters per second. So if I let that ball let go here and then it comes to you, it would reach you at 10 meters per second. It's kind of a lot like if you throw a ball up in the air at 10 meters per second, it will rise to a particular height. If I drop that ball from a particular height and it comes down in my hand, what's its velocity? 10 meters per second in the opposite direction. What goes up must come down with the same velocity. It's the same point as this. So instead of doing this to get velocity, all you've got to do is rearrange the equation and you can get the distance. And all you'd have to do is plug in all the values that we had before and you would get the same distance of whatever we set it to be, 0.1 meter. Because the closer that charged particle got to Q, the big Q, the stronger of a force it would feel to get pushed away, until eventually its velocity reaches 0, and then it would start to slide back in the other direction. So The last thing that I need to do to talk about potential, and we will make it to circuits, or at least some of it, is if I gave you, we're not going to do this, if Q1 equals 5 millicoulombs and Q2 is equal to negative 8 millicoulombs and Q3 is positive 4 millicoulombs, and there's something similar to this in one of the problem sets. And I asked to find what is the electric field at that particular point. Your proper response is, oh my goodness, please don't make us do that. Because what you have to do is you have to set up 3 different electric field lines and then add 3 vectors together. Now, adding 3 vectors together it's not hard, it's just cumbersome. It's tedious. But let's say I had the same 5 millicoulombs for Q1, the same negative 8 millicoulombs for charge 2, and Q3 is 4 millicoulombs. And I said, well, what's the potential, the total potential at that particular point? Given that R1 is equal to 0.1 meter, R2 is equal to 0.2 meter, and R3 is equal to 0.3 meters. For this, it would be, oh my goodness, it's a horrible thing. For this, if you see a problem like this on the test, just like I think there is one in the problem set, you should go, oh goody. Because potentials are scalars. They simply add. Like mass and moment of inertia. If you have a 2 kilogram mass and a 3 kilogram mass, and I say, how much mass do you have? You're not going to have to do any vector stuff with it. You just add the 2 together, boom. So the total V is just V1 plus V2 plus V3, or KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. And we get that. So all you got to do is, well, first I would factor out the K. I don't want to write that thing 3 different times. And you get that. And then you just write out 9 times 10 to the 9th, 5 times 10 to the negative 3 over 0.1. Now Q2 is negative, so you do have to take that into consideration. 8 times 10 to the negative 3 over 0.2 plus 4 times 10 to the negative 3 over 0.3. And then you just add that stuff up. Oh wait, I didn't do it right. 5 negative 3. And I get 2.1 times 10 to the 8th volts and positive. You can end up with a negative number, but all you have to do is just add them up. And a lot of people say, seriously, it's that easy? Yes, it is that easy. That's why a problem like this, if I gave it to you, it would be an appetizer problem. It wouldn't be a regular problem, because it's just that straightforward. You just add that stuff. All right, now we're gonna briefly start with circuits, and in circuits, we make the analogies of potential is like altitude, and current are to streams, and batteries are to water wheels that lift water. And resistors, the analogy that I use is waterfalls, or our waterfalls. So we've all seen a stream before. And so a stream has water passing through it. In fact, we've talked about it in like Bernoulli's equations. The bigger the stream, the more water going through it. The faster the stream goes, the more water going through it. That water, the analogy that I make to it, it's like current. Current is a fundamental unit. It is an ampere, or an amp. 1 ampere is 1 coulomb per second. So an ampere lets you know how much charge is passing through a point over a particular time. If 3 coulombs of charge passes a point in 30 seconds, current, which I use as I, some people use big I use little I. That little I is just the delta Q over the delta time. So 3 divided by 30 is 0.1 amps. For, in terms of scale, the current flowing through your heart to control it is on the order of a couple milliamps, microamps to milliamps. So if you deal with current on the order of amps, like the wires in your house, you can seriously mess stuff up. When you rub your feet along the carpet and build up a charge, and then you touch a doorknob and then current flows, that shock is basically a whole bunch of current passing through the nerves of your arms and your body, and that causes like the twitch, because what's happening is that the nerves are all firing simultaneously, and that's causing your muscles to contract. It's also another reason why you shouldn't pass current unnecessarily across your chest, because passing current across your heart muscles kind of depend on a regular, controlled current flowing through it. And just haphazardly just blasting current through it is a bad idea. So don't do that. That's why, so what happens with, they've got like the paddles, the emergency doctors, and what do? They put one paddle on your chest and the other one on your side, and then they go clear, and what they do is they fire a massive current jolt through your heart, and it's the equivalent of jump starting a car. It's trying to just seize up that heart to get it to reboot effectively. I've seen some people look at me quizzically, I don't know. I don't do English. I have an initial problem with saying that current is a fundamental unit. I'm willing to admit that mass, kilogram, is a fundamental unit. I'm willing to admit that seconds for time is a fundamental unit. I admit that meter is a fundamental unit of density, or I'm sorry, of distance. However, why isn't Coulomb a fundamental unit and current is? Current is coulombs per second. And so there is a fundamental unit of second. If that's fundamental, how can ampere be fundamental? And so it's really kind of a practical experimental way. You can show me a second. You can show me a meter. You can show me a kilogram. You can show me a dozen, which is the fundamental unit for count for the imperial system, or as one of my friends said, the freedom system. But for current, you can't show me a coulomb. You just can't go down to Walmart and pick up a coulomb of charge. But it is not easily measurable, but ampere is. And so that's why they say ampere is a fundamental unit, because it is the most easily measured quantity compared to all the other stuff that we got. So that's why I'm still a little bit ticked, but I will accept the reasoning behind it. From an experimental perspective, it's the easiest thing to measure. Okay, that's my rant. I get all tired when I rant. Let's see. In a circuit, we have several parts that we need to identify. That is, this is a battery. The plus is the side of high potential. The minus is the side of low potential. And what you will typically see is just V equals like 20 volts. You could write it like this. A lot of people write it delta V is equal to 20 volts. When you go down to Walmart, you just go pick up batteries and go, what battery is that? Oh, it's a 20 volt battery. You don't say the potential difference between the poles is 20 volts when you say 20 volts, but that's effectively what you're saying. Is that V there is letting you know that the potential difference from the negative side to the positive side is an increase . The delta V is positive V. If you go from high to low, the delta V is negative V. And if you notice, the high V, the vertical line is the bigger of the lines. For low V, it's the smaller of the lines. Also in a circuit, you have what is called a ground. It's the reference point. A reference point, it is the point where it and all adjacent wire has a potential that equals to 0 volts. So there has to be a reference. To make things easier, you need a reference point in your circuit. These reference points look like that. It's a vertical line with a bunch of horizontal lines that just get more narrow or shorter the further down they go. You can put the ground anywhere. Just like I told you when you were doing 1D and 2D motion, you could put the origin anywhere you want. But what do we know about how I pick my reference points? I put it in a very sensible location. I almost always put the ground at the negative end of the battery. So typically, if you see a battery that I've built, I will put the ground like that. And if I said that this battery is a 20 volt battery, that means that the potential on that side of the battery is equal to 0, and the potential at that side of the battery is equal to 20. Because you're setting the potential at that wire to be 0. And when you go from a negative to a positive lead on a battery, you rise up 20 volts, much like if you went up to a water wheel and the water wheel picks you up, you rise a certain distance. If we change it, if we do things a little bit more exotically, and I say that it's still a 20 volt battery, but I put the ground over there, which is an unusual way, but it's not incorrect. The potential over here is 0 volts, and the potential over there is negative 20. Because when you go from negative to positive, you're increasing your potential, and in order to increase 20 volts and reach 0 volts, you have to be at negative 20. And if you go from positive to negative end on a battery, you're going down 20 volts, which means if you start at 0 and you go down 20 volts, then you end up at negative 20. It's like saying the origin was the floor or the origin was the ceiling. If the origin is the floor and we go to the ceiling, we're at 20. If we set the origin at the ceiling and we come down, we're now at negative 20. So it's all about reference. But for sanity's sake, and when I work with these things, I've worked out a very specific way to do it. The thing that I almost always do, unless there is something bizarre that I have to figure out, I put that ground on the negative end. For the time being, this is the last part of the circuit that we're dealing with. The resistor. And it's just a line with a bunch of like little squiggles, a lot like the shirt that Charlie Brown wears, just that diagonal line that goes up to the right, down to the right, up to the right, down to the right. You could draw how many squiggles you ever want. And a lot of times if I'm in a rush, I just do that and it's the same thing. Resistors are made of many materials that control how the current flows. High resistivity. Resistivity is the material's ability to prevent current from passing through it. If you have high resistivity, you have low conductivity. And the best example that I have is like rubber. Very difficult to pass current through rubber. Metal, like wire, has low resistivity or high conductivity. And resistors fall in the middle. And it all depends on what you made it out of. Do you want it to have a higher resistance or a lower resistance? It depends on your needs for what the circuit's supposed to do. The big equation that we have to use is Ohm's law. And that is the current is delta V over R. That current is the ratio of the change in potential divided by the resistance. We know about current. Current is coulombs per second or amperes. We know voltage, potential difference, or potential. That is in volts. Resistors, they use the value ohms, or ohm for singular. And their symbol is a capital omega. Just as little omega stood for angular acceleration, big omega stands for resistance. So the equation that we're going to work with, I'm going to change Ohm's law just a little bit. Since delta V, the way that I kind of like how to do things is I like to deal with current magnitude and I make it V high, V low over resistance. So if I have a wire with a resistor on it, and the resistor had a resistance of 100 ohms, and one of the potentials is 10 volts and the other potential is 2 volts, I want to know what is the current and in which direction. Current flows from high to low potential. Much like water flows from high to low altitude naturally. current flows from high to low potential. So the current in this particular case will flow from left to right. And this is typically why I just use magnitudes. I look at it and go, well, there's a high potential, there's a low potential, so it's going to go from high to low, so the current in this case is going to go from left to right. So the current is 10 high, 2 low, divided by 100. So it's 8 divided by 100, or 0.08 amps. And that's the current flowing through the resistor. The last thing that I'll cover, it's a good thing to end on a little bit of a rant. We have learned that if you have a negative charge and you have a high voltage or a high potential on the left and you have a low potential on the right, in which direction is the negative charge going to move? Now remember, high potential is a lot like a hill. Low potential is a lot like a valley. High potential is like a positive charge. Low potential is like a negative charge. So which way does it move? It moves to the left. It moves to the higher potential. I've told you that current flows from high to low. Yesterday, what did we talk about? Electrostatics. In electrostatics, what was the thing that was moving all the time? The electrons. Did the positive charge move? No. In wire, in currents, in circuits, it is the electrons that move in the wire. The electrons are doing the moving. So if we're looking at this, one is at 2 volts, one is at 10 volts, ignore this for the moment. In which direction is are the electrons moving? They're moving from right to left. They're moving from low potential to high potential. So the electrons are moving from right to left. The current is flowing from left to right. So what really is happening is that the direction of the current is opposite to the real flow of electrons. Electrons flow in the opposite direction of current. Initially, who do we get to blame for all this? Ben Franklin and the other people who were playing with electricity at the time. They initially thought that it was the positive charges that were doing the moving within circuits. Then they figured out they were wrong. So all they did was they just kept the direction going in the same way, because if it was the positive particles that were moving, it would move from left to right. And then they go, let's just not change it and just say the electrons move in the opposite direction. So when you're thinking about current, current is just letting you know the opposite direction from where the electrons are actually flowing. We will continue with this on Wednesday. The second page of problem 2 will not be due until Friday. So everything on page 1 is due on Thursday. Have a good weekend. Don't die. Thank you. Yes.
I got an email about my attendance verification. I won't have my student ID until Monday. But
Did you sign the sheet of paper?
No, I did not.
Okay.
Should I